In this video, we are going to look at stress, strain, and the Young modulus. This video follows directly from the first one where I was talking about Hooke's law and springs. Please be sure to watch that one before going on to watch this one. The extension of a wire depends on other factors besides the tension, e.g. the diameter of the wire, its length, the material from which it is made. A longer wire stretches more than a shorter wire of the same material and diameter when loaded with the same weight, but the extension per unit length is the same. A thicker wire stretches less than a thinner wire of the same material when loaded with the same weight because the load is spread over a bigger area. So we're going to define tensile stress as the force per unit area applied perpendicular to the area. So it is basically the same as that definition for pressure. So tensile stress is given a symbol sigma is going to be equal to tension over cross-sectional area, F over A. The unit again is the Pascal, which is the same unit as for pressure. 1 Pascal is equal to 1 Newton per square meter. Then we're going to define yet another parameter called tensile strain. This is the ratio of the extension to the original length, or the extension per original length. So tensile strain is given the symbol epsilon, some say epsilon, which is equal to extension over original length, which is extension over the original length, E over L naught. Strain is a ratio, so it does not have any units at all. Then we have Young modulus. Young modulus of a material is the ratio of the tensile strain to the tensile stress. Sorry, the other way around. It's tensile stress over the tensile strain. So stress over strain, sigma over epsilon, going to give you force per unit area over extension over original length. And if you rearrange this, you're going to get FL naught over EA, provided the limit of proportionality is not exceeded. The unit of Young modulus is Pascal again, newtons per square meter. And the symbol for Young modulus is capital E, please. Then we move on to an experiment to measure Young modulus. Right, when measuring Young modulus, you need a very rigid support, a very rigid support where you hang the wires. Okay, you've got the 2 wires. So one of the wire is subjected to variable loads. So as you change the loads, the wire extends differently. And then the next wire has a fixed load, which just keeps the wire taut. And on this one, you have you do have a millimeter scale, and then on the one that is a variable load, we have a vernier scale, so that we take the readings of the extension. So both wires are supposed to be of the same length and material to eliminate errors due to expansion as a result of temperature changes during the experiment or yielding of the support, since both wires will be affected equally. Thin long wires are used to give measurable extension and large stress for small loads. The vernier scale enables the extension to be measured accurately, and the diameter of the wire is measured on several points using a micrometer screw gauge. Then you get an average value. Remember, when using a micrometer screw gauge, you measure the diameter spirally, that is around the wire, but on several points, so that you get an average value of the diameter to minimize errors. As the load is removed, the results are checked to see that the elastic limit has not been exceeded. So in other words, a graph, remember the only way you can see that is when you draw a graph of the extension versus the force, or the force versus the extension. the graph must strictly be a straight line passing through the origin. When it starts to curve, then you know that you've exceeded the elastic limit. So in this case, we are going to plot a graph of stress against strain. Stress on the y-axis and strain on the x-axis. The gradient is going to give you your Young modulus. Now, we know that, remember we are plotting a graph of tensile stress over tensile strain. So it's going to be stress is tension over extension, stress over, force over area. Remember from the formula here, right here, we had stress over strain, which is force over area divided by extension over original length. So FL naught over EA. FL naught over EA. FL naught over EA. So this is our F, L naught over EA, cross-sectional area. So that is it. So that's going to be Young modulus, and that's going to be equal to your 1 over gradient times L naught over A. We've just flipped this one over, and then we got 1 over gradient of that graph times L naught over A. Please let me know in the comments if you really want me to explain this further. I'm happy to shed more light on it. Example number 2 that follows from video number 1. Plot a graph of force that is on the y-axis against extension on the x-axis. Then calculate Young modulus using the gradient times initial length over cross-sectional area. Now these are the values that we have. The force here, and then we have the extension down, extension up. Find the average, you're going to get that. So you are plotting a graph of the force against the extension on the x-axis there. So I've done that, and this is my graph. I've plotted the graph. So this is force versus extension. So what I did is I used a scale of 50 50 newtons to represent 2 centimeters there on the graph grid, and it's going up to 392.4 right here. So which means here I should have 400. So it will be 50, 100, that and that and that, up to 400. Then on the x-axis, I must end at 5.06. So again, I use 0.5 to represent the 2 centimeters on the grid. And then right there, I have 5.5 right at the end. Now, just to go over your paper 3, sorry for digressing a bit, make sure that the graph occupies at least 50% of the total graph grid. Make sure that when you plot your points, they are x's. I think this is not visible on there, but there are small x's here, so that I do not get blobs from there, because you may lose marks for that. Make sure also that you label, okay, your x's should be correctly labeled. Use a suitable scale that is multiples of 1, let's say 1, 2, 3, 4, 5, that's all number integers, or 2, 4, 6, 8, 10, 12, or 0.2, 0.4, 0.6, or 200, 400, like that. Or you can use 0, 5, 10, 15, 20, like I've done here, or it could be 0.5, 1.0, 1.5, and so forth. So those are the three that you can use: 0, 1, 2, 3, 4, 5 multiples, and then you've got 2, 4, 6, 8, 10, then I've got 0, 5, 10, 15. You can't use awkward scales like 0, 7, 14, 21. It will make it difficult, or for you to find a point that may lie between two big squares. So in this case, I've plotted the graph, and then as you can see, my points are very close to each other, very, very close to each other. So that's what's supposed to be the ideal, because when analyzing your data in the paper 3, they will also look at the relationship between your points. If at all there are two or many points that are far away from the line of best fit, then a mark may be deducted. Now we are supposed to find the gradient. So when I found the gradient, that was 350 minus 0. So this 350 point lies exactly on the vertex of a big square, and then corresponding to 4.5 right there. So I used that to calculate my gradient, and I found it to be 7.78 times 10 to the power of 4 newtons per meter. Now from this question, they said find the Young modulus using gradient times initial length over cross-sectional area. Gradient times initial length over cross-sectional area. So the gradient, I found it to be 7.78 times 10 to the power 4 times 2.58, that's the original length, over the area, which is pi d squared over 4. Okay, so diameter is 0.36 millimeters. So I converted that to meters, and I found 0.36 times 10 to the power of minus 3. That's that one today. Multiplied by that squared, that one, and then divide by 4. So pi d squared over 4 is what we always use as our formula for area. Right, example number 3. A load of 20 newtons on a wire of diameter 1.0 millimeters produces an extension of 0.1 millimeters. If the length of the wire is 3.0 meters, calculate the tensile stress and the strain. And then 2, find the Young modulus. Now remember, stress is equal to force over area. The force is 20, the area is pi d squared over 4. Okay, and let's see, pi d squared over 4, this one, yes, diameter 1 there. So it's going to be, in this case they use 0.5, no harm in that. You still get the same answer, which is 2.5 times 10 to the power of 7 pascals. Then strain is equal to extension over the original length, which is 1 times 10 to the power of minus 3 converted meters, divided by the original length, which is 3 meters. So you get that. So Young modulus then becomes stress over strain, which is 7.5 times 10 to the power of 11 pascals. Now I want you to know that your Young modulus must always be in the region of order 10 to the 11, 10 to the 12, thereabout, 10 to the 11, 10 to the 12. Then you know your answer is correct. I'm going to end this video by looking at elastic and plastic deformation. Elastic and plastic deformation. Now, if we draw a stress-strain graph, right? Like I said, like the example that we did there with the stress-strain graph, we said the gradient is the Young modulus. Right, so the limit of proportionality is shown there as P. Right, so that's where strictly the force is directly proportional to the extension. So in that region, strictly the force is directly proportional to the extension. Now beyond the elastic, so the proportionality limit, slightly above it, the graph starts to curve, but just slightly above that, that's where you've got the elastic limit. Okay, so when you say elastic limit, we don't say, it's not strict that is directly proportional. Where you have the proportionality limit, that is where that is below the limit of proportionality. Then after that, you've got the yield point 1, and then yield point 2, and then after that you've got the ultimate tensile stress, and then after the ultimate tensile stress we get what is called the breaking point, which is B there. So from 0 to the proportionality limit, the stress is proportional to the strain. The proportionality limit, or the limit of proportionality, is the maximum load or tension in the wire when the extension is proportional to the load. The gradient in this section equals the Young modulus. Then the line curves beyond P, continues past the elastic limit to the yield point. The elastic limit is the maximum load or tension which the wire can experience and still regain its original shape and size after the load has been removed. Beyond the elastic limit, the wire is permanently stretched and suffers plastic deformation. So beyond the elastic limit, you now have plastic deformation going all the way there. So we define a plastic change as a change where there is no permanent deformation. That is, when the load is removed, the object retains its length, shape, or size. So note that elastic does not mean that the extension is proportional to the load. Like I said, the extension is proportional to the load within the limit of proportionality, not the elastic limit. Then we've got yield point 1. This is where the wire weakens temporarily. Beyond Y2, a small increase in the strain, a small increase in the stress causes a large increase in the strain. So as you can see, the small increase here in the stress, so if you can see, you just move a small bit here, but then the strain becomes large. So a small increase in the stress produces a large increase in the strain. So this is the dominant area for plastic deformation. That's where you have ductile materials, or those materials that can stretch. So yes, so this is plastic deformation. The maximum stress which can be applied is called the ultimate tensile stress, UTS. Beyond the UTS, the wire loses its strength, extends, and becomes narrower until it breaks. So you actually see it necking. It becomes thinner and thinner around the area where it is going to break. So we call that necking. So the stress at B is called the breaking stress. So beyond there, when necking occurs, beyond there we're going to get breaking. So the breaking point will be at point B. I hope that makes sense to people. Now, stress strain curves for different materials. Steel is stiffer than copper. As you can see, remember we said stiffness refers to the, if we have K, the force constant. If it's not a spring, it's called force constant, but if it's a spring, it's called spring constant. So force constant will be the force per unit extension. So high values of a force per unit extension give rise to stiffness. So it means steel being stiffer, it has a gradient, a larger gradient, or the largest gradient of the three. The gradient of stress strain for steel is greater than for copper. The gradient equals the Young modulus, so it has got a greater Young modulus steel. Then glass. The elastic behavior of glass is shown up to the breaking point. It has no plastic deformation. So beyond the elastic limit, the glass breaks right away. So such materials are said to be brittle. Materials which show large amount of plastic deformation are ductile. Like I talked about that, where you have got a large plastic region before breaking. So copper is an example of a ductile material because it stretches. And ductility is the ability to be drawn into a wire. Steel is stronger than copper because its UTS is greater, ultimate tensile stress. So the ultimate tensile stress is, remember I said this is the maximum stress before breaking. So maximum stress for steel is right here, and then maximum stress for copper is right there. So the maximum stress before breaking is less than that for steel. So ultimate tensile stress for steel is bigger. I think I'm going to end the video here, and then in the last video I'll talk about elastic potential energy, or energy stored per unit volume, etc., etc. Please do comment in the comment section and let me know in the which areas you are struggling with, and then I'll be happy to help. Signing out.